Okay, so let's question on some notation. That notation's in the text, so if you read the problems and don't understand the notation, go back to the text section, see if you can understand the notation. Or if you want a quicker answer and don't have anything better to ask in class and I'll tell you. Fair enough? Well, you just ask, so I'm telling you. So, to clarify the notation, which again, read the text section and find that it's consistent. It's the same notation. If it's not, come back and tell me. You can always change the notation of the problem set. Since I was looking right at the text problems when I adapted them, I'm pretty sure that my notation's likely to be consistent. Okay. Okay, anyhow, your general differential equation, first order differential equation in x and t is this. Okay? This is some function of t and x. The derivative is some function of t and x. Okay? So there we have it. Now we see that this, in this case, it's a nonlinear equation because you got x squared. Okay? So it's not even a question whether it's homogeneous or not. It's nonlinear. It's a mess. And we might not even be able to solve it in closed form. Okay? As soon as you get into nonlinear, things get difficult. But we can always do numerical approximations, and that's what this problem's talking about. Okay? So, when we do a numerical approximation, we do steps. We say, okay, here's our starting point. That's your initial condition. So maybe we started over here someplace and said, okay, now we're going to go in increments of delta t equals 0.01. Right? So we start here, we figure out what the slope is at this point just by plugging in the coordinates of x and t. We get the slope, we move over that far in the t, we move up or down according to what the derivative is, right? And we understand that because it's the first thing we did on the first day, I'm pretty sure. The whole idea also underlies most of the proofs of existence and so forth. It needs to be refined. You need to consider exceptional cases. You need to, so you need to be very rigorous in proving these things. Okay, but this is very important. And this is also Euler's method, and you can symbolize it, removing all understanding from the whole process, and just write symbols and tell a computer to do it, because a computer doesn't need to understand anything. Okay? You're not going to be very good at doing that unless you understand what's going on, but fortunately what's going on is very simple. Okay, and what's going on is after k steps, you've migrated around and you ended up here. Okay? So what are you going to do next? Well, you have your increment delta t. It's always the same for every step. Now, you can modify the method if you understand it. And looking at the function f, you can say, when I'm in certain regions, I'm going to reduce delta t because things get a little weird. But in this region, things are pretty predictable, so I'm going to increase my delta t to increase the efficiency of your algorithm. Okay, so there are all kinds of things you can do with that, but right now we're just looking at what happens for constant delta t. What do? Here's our point. What's the slope of the graph at this point? Well, plug in the x and t coordinates here, right? Which means you evaluate f of t sub k, x sub k. Evaluate this at this point, and it's the same as saying x prime equals whatever you get here if you plug xk and tk in. Okay? Okay, so here's your point. Your slope is f of xk tk. And you're going to project by moving this far in the t direction. You project along this line segment to get your xk plus 1, tk plus 1. And then you just write down what that is. Okay, so again, without worrying about all the details, at the very surface level, the most superficial level, your next value of x is this value plus the slope times delta t. Okay? You don't have to think about derivatives or anything. And there's no derivatives to be involved here. Okay? The only way the derivative is involved is that your slope is f of xk, tk. Actually, I've got t first. I'm not going to correct it. Probably should reverse these, okay? But you evaluate this function f at this point. It's too bad. I got to fix it. Even if it's a smudge, I got to make it right. Okay. Make sense? And you multiply that by delta t. Now, you could so right there is how you go to your next step. And of course, you want a formula for t sub k plus 1, which will be what?
T sub k plus slope times, right.
Tk plus 1 has no dependence on slope. Let's picture, how much did t change?
Delta t.
Which is now h, right?
Yeah, so it's t sub k plus h.
There it is. That's the whole Euler scheme. Other things you've got to be careful about. You better not try to project across an asymptote, but we talked about that on the first or the second day. So there's nothing here that you haven't seen, it's just the notation. And that should allow you to proceed with that problem without any trouble. Okay?